We are once again in Math 432, Applied Combinatorics, and I am Professor Asaph. The topic of this series is the binomial theorem. We're going to start it with a concrete example, and we're going to relate it to the binomial coefficients that we had before. If you remember, we had these 4 bugs, and we thought about how many ways we could choose 2 of them. And we figured out there were 6 possible ways. We could choose the red, and then there were 3 things that we could choose with the red, so that's 3. Plus, if we didn't choose the red, we could choose the blue, and there were 2 options there. So that gives us 2 more options, which makes 5 total. Or if we didn't choose red or blue, there's only 1 option, which is these 2. So that's 6 options in total. So let's think about expanding this term out. I'm going to think about it term by term. I've got x plus y times x plus y times x plus y, and one more color, x plus y. Now, if I wanted to, I could actually go through and multiply this out using the FOIL method, but I really don't like doing that. I'm looking for a shortcut. So the shortcut I'm going to look for is I'm going to think about what terms are going to show up. There are only so many things that can show up. I can't get x to the 5th, for example. In fact, I know that because each of these is degree 1, right? I know that whatever I'm going to get is going to have total degree 4 because there are 4 terms. And I'm either picking the x's or I'm picking the y's. So I can think about what are the terms that are going to show up. Well, I could take all x's, or I could get 3 x's and a y. That's another way to have degree 4. I could get 2 x's and 2 y's. I could get 1 x and 3 y's, or I could get all y's. Now, without knowing how many of each I get, I at least know that these are the possibilities that I'm going to get. So let's look at a specific example here, and let's say, how could I end up with x squared, y squared? What are the possible ways that I could do that? Well, it's actually the same thing as choosing my bugs. I can think of each bug as, say, picking x, okay? So if I take the bug, I take the x. So when I choose 2 of these bugs, for example, if I choose these 2, that's telling me I take the red x and the blue x. If I choose the blue and the green, then I'm taking this x and this x. Now, when I don't take the x's, so suppose I did take these 2 x's, what's left? Well, that means if I'm not taking these 2, then I have to be taking the y's. Otherwise, I would get the x. I have to take one or the other. So this coefficient right here is actually the coefficient that we already counted. I've got 4 bugs, and I choose 2 of them. And the same way, if we want to make it a little more concrete, so this was our bug selection problem. Maybe I'll leave the bugs here for this. I guess they're all the bug selection problems, so maybe the bugs can just stay over there. This is because we choose 2 terms for x, and then the rest for y. Now here, if I'm taking x to the 4th, that one's even easier to see, because what do I have to do? Every time I have to pick all of the x's, so there's only one way to do that. Well, 1 has many different ways that we could write it. 4 choose 4 is one of the possible ways to write the number 1. Take everything. So take all the x's. Here, I choose 3 places to take the x, and whatever's left, I take the y. So I could say that's 4 choose 3, and then whatever's left, I take the y. For this paradigm, I'm going to choose one of these. There are 4 options, so I'm going to get 4 in total. One possible way to write 4 is with this binomial coefficient. And if I want y to the 4th, I never take the x. So this is what I get. And then in the end, what are we left with? Well, there's nothing special about the number 4. So what we have is the binomial theorem, which can be stated as x plus y to the n is the sum from k equals 0 to n of n choose k, x to the k, y to the n minus k. Now there's an important thing here, which is that I made a choice here that I was always choosing with x. And actually, if you look here, I've noticed I've written mine backward. I've replaced x with y. So let's justify that. So let's notice there's a symmetry between x and y, right? This formula seems to say x gets the k and y gets the n minus k. But over here, it doesn't matter. Addition's commutative. So why is that the case? Well, n choose k is the same as n choose n minus k. Why is that? Because choosing which terms I take the x forces my choice for the y. So if I choose k of them to be x, the other n minus k have to be y. So we can prove this identity in a couple of different ways. So let's do a combinatorial proof first. So proof 1, and this will justify that my example actually matches the formula here. Proof 1 is we can choose a k element subset by choosing what goes in, that's the left-hand side, or by choosing what is not in, and that's the right-hand side. So the ones we don't want or the ones we want, either way it determines the set. Another way that we could see this, that's a nice combinatorial proof, we could see it from our formula that we had before. N choose k, what is that? Well, it's n factorial divided by k factorial n minus k factorial, which is the same thing as n choose n minus k. Notice that in both of these, the two terms in the denominator without the factorials add to n, so algebraically, this identity is true as well. This is an often useful way to rewrite this formula depending on what your use case is. Next, we'll look at some applications. We can get a lot of mileage out of this binomial theorem by plugging in clever values for x and y. Or if we think about how we prove the binomial theorem by interpreting this as making choices, then we can come up with really interesting identities and combinatorial proofs for them based on the combinatorial proof of the binomial theorem that we've just seen.